In this video, we will talk about how to determine if one vector is in the span of other vectors. So let's say we have the vectors u, v, and w, and we want to know, is w in the span of u and v? Well, another way to phrase that is, can w be written as a linear combination of u and v? Or in other words, can we write c1 times u plus c2 times v is equal to w, where c1 and c2 are just constants? The way that we can figure this out is that we can place u, v, and w all into one matrix and then convert that matrix to a row echelon form. So here's what that would look like. The first column of this matrix will have the values from u, so we'll say 1, 1, 1. The second column will have the values from v, 3, 2, 1. And the augmented column of the matrix will be the values from w, 2, 3, 4. Next, we need to convert this matrix to row echelon form. So recall in row echelon form, if we have a pivot entry right here, or in other words, a non-zero value in the first row, we want all values below that pivot to be 0. So how can we make this one a 0, and how can we make this one a 0? Well, notice if we just do row 2 minus row 1, that would be 1 minus 1, which would make this a 0. And similarly, in row 3, if we just did row 3 minus row 1, that would be 1 minus 1, and that would make this a 0. So we can do both of those operations at once. So we'll say row 2 is going to become row 2 minus row 1. And row 3 is going to become row 3 minus row 1. So here's what that matrix looks like. So the first row doesn't change at all. We'll just write those values 1, 3, 2. Row 2 is row 2 minus row 1. So 1 minus 1, 0. 2 minus 3, that's negative 1. 3 minus 2 is 1. And in row 3, we have row 3 minus row 1. So 1 minus 1 is 0. 1 minus 3 is negative 2. And 4 minus 2 is 2. Okay, so here's our first pivot entry. Here's our second pivot entry. It's the first non-zero value in the second row. Remember, in row echelon form, we want all values below the pivot entries to be 0. So we need to make this negative 2 a 0. So we could say row 3 minus 2 times row 2, because that would be negative 2 minus a negative 2 times negative 1, which would be negative 2 plus 2. That would make this a 0. So we'll say row 3 is going to become row 3 minus 2 times row 2. So let's see what we get. So the first row doesn't change at all. We'll just write those values. And the second row doesn't change at all, so we'll rewrite those values. Now in the third row, we get 0 minus 2 times 0, that's 0. Negative 2 minus 2 times negative 1, that's negative 2 plus 2, that's 0. And then we get 2 minus 2 times 1, so that's 2 minus 2, which is also a 0. So this matrix is now in row echelon form. Now, once it's in row echelon form, the first thing that we want to check is, does this represent a consistent system? Well, in this very last row here, we can see that we have all zeros. And that's perfectly valid because 0 times a number plus 0 times another number is going to be equal to 0. The only way this would be an inconsistent system is if we had something like 0, 0, and a non-zero, like if we had a 4. Because 0 times something plus 0 times something could never equal 4. So that's the only way this could be an inconsistent system. So that's good. This system is consistent. Next, we want to see if we can write this in the form with C1 and C2. So I'm going to rewrite this matrix over here and make a little room. Okay, so if we were to write this system of equations in terms of C1 and C2, here's what that would look like. 1 times C1 plus 3 times C2 is equal to 2. And the second equation would be negative 1 times C2 is equal to 1. So we need to solve for C2 and C1. So C2, we can see that has to be equal to negative 1. A negative 1 times a negative 1 is equal to 1. Now if C2 is negative 1, we can plug that into this first equation. So we get C1 plus 3 times negative 1 is equal to 2. So this is a negative 3. We can add a 3 to each side and find that C1 is equal to 2 plus 3, that's 5. So we solve for C1 and we solve for C2. So it turns out that we can write W as a linear combination of u and v in this manner. We'd say 5 times u minus 1 times v is equal to w. And if we want, we can double check that this is the right answer by seeing if we can say 5 times the values in u minus 1 times the values in v actually equal the values in w. So here's what that would look like. So let's check. We have 5 times 1, that's 5, minus 1 times 3, so 5 minus 3, that does equal 2. Then we have 5 times 1, which is 5, minus 1 times 2, so 5 minus 2 is 3, and 5 times 1 is 5 minus 1 times 1, so 5 minus 1, that's 4, so that checks out. So as our final answer, we can write yes. W is in the span of u and v, and that's because we were able to write W as a linear combination of u and v.